Hi, so my partner and I had created Barefold. So what is Barefold? So first, this is what we created. What essentially we're trying to create is a clothes folding machine, because we're thinking that we would like to spend more of our time doing things that are more fun, and we thought, why not combine ME1 and 2B to create a solution that can help us fold our own clothes. We thought it'd be kind of cool, and this is what we came up with. So we're going to review this picture later on. So first, what are we and what did we do? So what we try to do is we try to create an automated solution that would act as like folding the panels like this, but also be a little bit more robust and functional than like currently over here, but would be cheaper than this professional solution. So that's why we tried to create Barefold this semester. So this was the original idea. The original idea was to have this like a different kind of panel layout. And what it would do, it would be like act differently depending on if it was a shirt mode or pants or short mode. So this one would fold, and then this one would fold, this one. Eventually, it would fold on this last panel. What we found though, so this is our CAD initial drawing. But then this is what ended up happening. So this is our concept CAD for what happened and why we went from here to here. I'll explain later. This one is the final CAD, and we ended up going with one panel design because we figured that it can showcase this design while being still being cost effective, but also still showing the function and what we learned in ME102B. So the reason why we went from this design, and we transferred into this panel is because we found out the size of this would be too large compared to just using this panel design. So we ended up using this panel design. So this is our state diagram, and here you can see that we have 5 main states: armed, folding modes, and warning. What would happen is that the user would turn on the machine, it would be armed, and there would be a potentiometer that you could change, and the potentiometer would affect how much pressure would be applied to the panel. If they press one of the 3 buttons, you would go to the folding modes. But if there's a current sensor, and if the current sensor detects that there's too much force being applied, then you would go straight into a warning mode. Users can't change this mode right here, and then you would go directly back to a frozen kind of warning mode until the extra pressure is not applied anymore. Then you would go back to this arm mode, and you can continue pressing the buttons. And this is just our circuit showcasing this. The only thing that it doesn't showcase is the current sensing mode. This is what the circuit might have looked like with current sensing. These are the current sensors, and these are the motor drivers. This is an INA 219, but essentially it's the same thing. You have microcontroller, you have 3 buttons, but in this case you have 3 motors, because this one would be for this CAD, but because we were designing for this one, which ended up looking like this is what our final circuit would be. But still same functionality. So let's go back into what we designed then. So this is what we designed. So essentially we wanted to have some kind of transmission that would easily lift off the panels, so it would have enough force and get enough mechanical advantage, but at the same time be rigid enough and provide enough speed so that the clothes just don't slide off the panels. So we ended up going with a crank rocker mechanism, and this is what we got. It was derived using Grashoff's conditions, and this is our transmission. And this is what we learned from ME102B, based upon ME102B. We have our motor. We have a shaft coupler connecting to this D shaft, and the reason why we want to have this whole mechanism is first in order to actuate this linkage, but also there are some sleeve bearings, and these sleeve bearings help alleviate the load acting at these internal bearings of the DC motor. So we have this D shaft, and there's a shaft collar right here and right here. These shaft collars are to prevent axial movement of the system, and they work by friction. And since we don't have any radial loads, we figured having these shaft collars would be okay. Then we have here the sleeve bearings. The sleeve bearings act as ball bearings, except that they're just no balls. And this helps us because we didn't have to spend money on ball bearings, and with it, bevel washers and regular washers. And those washers are usually to preload the ball washers, but since these are sleeve bearings, we don't have to have any of those. Okay, so now I wanted to go into the building phase of this whole system. And one of the things that we want to highlight is just the general prototyping. So what happened here is that we had to 3D print our own brackets. And with these 3D printing brackets, we learned that you have to account for tolerancing in order to get the right fit. So if you print a direct fit, you don't necessarily get the it to fit correctly in the D shaft. In fact, the D shaft wouldn't even go in the holes at first. So we had to print multiple prints in order to see the correct holes. And this is with everything. So there's like the linkage, or not linkage, the D shaft with the 3D printed brackets, and they fit nicely. And there's a nice loose fit. Then we also laser cutted our own panels. In Jacob's Hall. And the problem with what we found with laser cutting is that actually we found out you get kerfing from the laser cut, and so we had to account for the width of the laser, and also just to get the nice fit that we wanted. We found that for the outside, we were able to get the nice fit using just glue, but in terms of the these holes, we actually had to account for first how to mechanically constrain our shaft, D shaft. So we decided to print these D-shaped holes, but then these D-shaped holes had to be further prototyped and iterated to have a nice interference fit so that the shaft won't move. Also, we had to design this mechanism at first to avoid interfering with other pieces, and we only found that after we further made the CAD. So this is the problem that we had with the D shaft. So because it was a loose fit, even with the shaft collars, it wouldn't move. And we tried reprinting it with the same hole, and eventually it would still slip. So we had to iterate in order to get an offset of 0.08 inside the CAD inches, and now it's a tight fit. That's just the picture of the motor with the shaft and the collar. And now if you look here, you can see that it does actuate quite nicely now. It doesn't slip anymore. These are the sleeve bearings, 3D printed brackets, shaft collars, shaft coupling, motor, D shaft. Okay. And then this is the final print. I made the piece. This is what the side view looks like inside Jacob's Hall. This is after we got it to work with the D shafts. And this is the circuit, which is actually right here. And I'm going to showcase how it demonstrates with the modes. Okay, so if you see right here, these are the buttons. If you press a button, it should... I'm going to demonstrate the different modes. So this is shirt, pants, shorts. Pants and shorts should act the same. Shirt should act differently. So depending on what button I press, the motor will behave differently. So for shorts, and we see that in here, it does say shorts mode. And now it says it's finished. That's to replicate that the mode has stopped. Now, short pants mode should be the same thing. And it is. And then it says pants mode. Eventually it says it should stop. Stop. Okay, now shirt mode should act differently. There, shirt mode is now activated, and then it says shirt mode. It behaves differently. Now it's stopped.